Artificial intelligence has moved out of the laboratory and into the physical world, from surgical theatres to bank loan departments. These models now play an active role in high-stakes human outcomes. When an algorithm manages a medical procedure or a mortgage application, the consequences of a failure move beyond digital errors and into tangible, life-altering risk. Public perception often labels AI ethics as a layer of bureaucratic friction, a set of rules intended to restrain the pace of technological development. High-performance brakes on a Formula One car serve a specific engineering purpose. They allow the driver to navigate tight turns at the highest possible velocity while keeping the vehicle on the track. Without that control system, the engine's power would be unusable. In a real-world race, the brakes enable the speed, they do not fight it. Ethical guardrails function in exactly the same way. They provide the technical stability necessary to deploy AI at a global scale. For an engineer, the challenge lies in converting abstract human values into precise executable code. The first pillar is fairness. Feeding historical data into a neural network often includes decades of human prejudice represented by skewed distribution graphs. The model perceives these historical imbalances as mathematical rules, amplifying the patterns and making discrimination part of its internal logic. Correcting this requires bias mitigation, active algorithms designed to audit and balance data distributions before the model is ever deployed to the public. The second pillar, transparency, addresses the black box problem. This occurs when a complex model reaches a conclusion without revealing the steps it took to get there. In regulated industries like medicine or banking, the computer reached this decision is an insufficient answer. Professionals must be able to verify the underlying reasoning. This is solved through explainability, engineering the model to map its own decision pathways so a human operator can audit the logic for errors or logical gaps. Pillar 3 is privacy. AI development requires massive quantities of data, which often conflicts with an individual's right to digital boundaries. To manage this, developers build secure consent framework architectures that prevent unauthorized scraping and ensure sensitive personal information cannot be leaked or extracted by third parties. Finally, there is accountability. When an autonomous system makes a critical error, we have to know where the liability rests. This schematic shows the link between the developer, the corporation, and the operator. This is a systems design question. The chain of responsibility and the manual fail-safes must be integrated into the product architecture before the power is ever turned on. These protocols move AI from an unpredictable experiment into a stable, commercially viable technology. Deploying a powerful system without these guardrails carries immediate risks and intense public backlash, and the potential for severe regulatory fines. But the long-term risk is the erosion of trust. If a technology is perceived as opaque or biased, the marketplace will eventually reject it. Raw processing power can generate interest, but only ethical alignment can create the stability required for production-grade integration into society. This requires treating these 4 pillars as primary technical requirements on the same level as processing speed or memory efficiency. As the capability of our algorithms increases, these engineering standards provide the necessary framework to ensure our most powerful tools operate safely and equitably.